The y-intercept? How do we know where that y-intercept is? We talked heavily about this yesterday. 0 in the x over chi. How do we know where that y-intercept is? The 0 in the x. Desiree, how do we know where that y-intercept is? 0 in the x. Now, we'll ask this, and this is important. Is that the first thing I should have looked at? Naisha says no. Z, did you say no as well? Okay. Naisha, what should I have looked at first? I need to know the type of function, don't I? Okay. We've got to know that type of function. Okay. Patient, I need to step out or go see Miss Jefferson. It's okay. All right. Can you go outside? Do you not need to? You good? Okay. If you need to, just let me know. Okay. So we need to look at that y. We need to look at that rate of change to figure out the type of function. What should we see in that rate of change there? Is it adding 6? Remember, I always need to go from the negative to the positive in my x, right? So I'm going from 20 to 14. Is that adding 6? No, that's adding negative 6 or just subtracting 6. But I've got an important question for y'all because I see a lot of 6s along here. Well, first off, it is subtracting, so we should know it's what type of function. Linear, right? So I'm using this equation or the a plus bx, either one. But I got to tell you, I don't see a single person with the correct rate of change up here. We have that minus 6 is correct in that it tells us that it's an additive, constant additive rate of change. But what's that constant additive rate of change of a line called? Look at that equation. Which part of that is my constant additive rate of change? Remember, the x is a variable. The b only happens how many times? Once. Remember, and if we did the a plus bx, right, it would be the b. But remember, it's not about a letter, it's about that multiplication, because what is multiplication? Repeated addition, right? But what's the name of that repeated addition, that constant additive rate of change? It's called a... We don't know what that M symbol stands for. Ooh. We gotta say again? Slope. Guys, remember the name of this is slope-intercept form of line. That is my slope. How do I calculate slope? Or
y over
change in y divided by change in x. Remember, the rise is my y values, right? Jalen, you engaged in this? Okay. Rise is my y values. Run is my x. That minus 6, that's my change in y. What's my change in x? What's happening to those x?
plus 30. Plus 30.
So what is my slope actually?
Negative 6 over 3.
Say that one more time. Negative 6
Over
divided by 3, which is? Notice I made the table like this, but I could have gone here. Every time the x is changing by 1, how much is the y changing by? Minus 2, 18, 16, 14. Does that get me to the same spot? Going by 2's like that? So is it accurate to say minus 6? It's minus 2x. This is why we have to remember that change in y divided by change in x. Guys, when it's constant additive rates of change, you have to pay attention to that change in x. I'm not going to give you a change in x that's different than 1 for exponential or quadratic, but I will do it for linear because you have to know slope is the change in y divided by change in x. That is an important piece of this. Again, we're getting better at recognizing, hey, it's linear. We're recognizing that constant additive rate of change. But I do see people still, not there, not there. I saw someone earlier, I do see right here where someone did 6 raised to the x, but remember, if it's a value raised to a variable exponent, what does that variable exponent tell me? Repeated what? Multiplication, right? that we don't want a variable exponent here. That tells me repeated multiplication. When I look up here, these top two answers, right, another variable exponent, 14x minus 6. What is this telling me is repeatedly being added? 14, right? That multiplication is my repeated addition. So we can't be doing that here. We got to pay attention. This is doable, but we got to pay attention to our notes on those things. I will hopefully have our Venn diagrams and everything else back to y'all tomorrow. It's just grading takes a while. Yes, Jalen? Those two equations? Can you write the equations down instead? You could use your iPad to take a picture if you want. Remember, there's also paper up here whenever you need it. But we don't have the phones in class. All right, so what are your questions about writing that equation before we continue? I know we still need practice with it, but we're going to use the bell ringers to do that practice. Jayla, you good now? Sanaya, how do you feel about writing that equation? You going to be able to rock it tomorrow? Okay. We have a bell ringer tomorrow where we have to write an equation. The what? This right here? Well, remember, the slope is the change in y divided by change in x. The change in y was negative 6. The change in x was a positive 3. And what is this fraction bar? That's why I don't want you all to say over. I want you to think about the division. It is division by 3. Yes, Jalen? Oh, I'm not erasing yet. You're good. All right. So let's look at our agenda for the day. So I meant to do this yesterday, but we had a nice heart-to-heart conversation about class. But I do want to celebrate the fact that it is Black History Month. We're going to talk about famous black mathematicians once a week. Just to give you all a picture of some of the people that have paved the way that it does happen. And so we're going to wrap up a couple of small details out of the book after that. And then we need our iPads with us today for sure. Who does not have their iPad with them? Why don't we have our iPads? Oh, you weren't here yesterday, Mickey, when I reminded everybody. But you were supposed to have an iPad yesterday, you're supposed to have it today. We gotta have that stuff with us. It's going, I will say this, you'll be able to see, guys, even if you don't have the iPad, the stuff out of MATHia. However, if you don't have your iPad today, that means you're gonna have more homework at some point because you won't be able to do the activity online. Yes, sir?
What is MATHia?
So the textbook that we have, Carnegie Learning, has an online component called MATHia. You'll be able to access it through Clever.
Is it something we do like classwork?
We will do some of it in class, and I'll give you all probably 15 minutes or so every couple of days. And it's not something you're going to have a ton of every day, but we're going to do some today in class. Yes, sir. Yes, ma'am.
Sure.
I was just thinking, Marcia, what's up? Say again. I put some in yesterday, but I got to finish grading. Okay. After that, we're going to get to Desmos, which, again, we need our iPads for Desmos, but that activity you can look on with somebody else if you need to. All right, so made a separate slide for Black History Month. Quickly looking at this. Okay, so famous black mathematicians for Black History Month. We're going to go over one mathematician every week. My goal is to do it on Mondays, but obviously we didn't do that yesterday. I just want to celebrate the amazing contributions of black men and women in the fields of mathematics. And here are the four that we're going to talk about. Benjamin Banneker, Katherine Johnson, Fern Hunt, and Mark Dean. There is at least one of these that's a little bit more famous than the others. Do y'all know which one?
Katherine Johnson.
Yeah, what was she involved with?
NASA.
NASA, right? We're going to talk about that. Hidden Figures, I think, is the movie that celebrated her. But Benjamin Banneker is the first one here. Let me turn the lights out. So Benjamin Banneker was alive during a time when black men and women, at least in America, really did not have a lot going on. However, he was a primarily self-educated mathematician and an astronomer. He was the first man to build America's or a clock in America at the age of 24, and it was a wooden device, right? It just struck hourly, but that had not been done before, so it was pretty impressive. But he used his understanding of mathematics and astronomy to make forecasts. Now, here's what I want us to focus on. I do want you to learn about right here. This is what drove him, and this is what can help drive you as well. And this is something we want to learn from him 100%. Whether you're white or you're black or anything in between, his deep curiosity and his understanding of mathematics paved the way years before any other black mathematicians in the U.S. Please understand, I can't give you that drive, that desire, but I'm going to try to do my best to give us things that can help us be successful. But at the end of the day, it's your curiosity about the world that's going to help you be successful. Math is the study of patterns and relationships, and if you haven't noticed anything else in the world around you, the world is patterns and relationships. Whether you've seen it through a mathematics lens or not, there are patterns and relationships. So if you start asking questions about the world around you, you're going to start to see those patterns and relationships. But you have to develop your understanding of those mathematics to be successful with them, right? So very impressive work by Benjamin Banneker, 1731 to 1806. Definitely lived during a very historic time period, but he did some impressive work with mathematics, and that helps him with astronomy. Oh, and I didn't mean to mention this. What you'll find out a lot of times is that mathematicians are not purely mathematicians, especially historical ones, because they usually developed or discovered the mathematics to help them talk about the world around them. Benjamin Banneker, what was his motivation for learning math? It was all about what? Astronomy. I don't want to talk about this guy because I feel like it slightly detracts from Black History Month, but I do want to put it into some more context. Does anyone know probably one of the most famous mathematicians of all time? So he was a physicist, and he did do a lot with mathematics as well because of physics, but actually the person I'm thinking about is another physicist. He lived in Europe. He developed 3 laws of motion. Isaac Newton, okay? So Isaac Newton actually developed or discovered the idea of calculus, which is a branch of mathematics you can study in high school, but the whole motivation for calculus was to be able to talk about physics, right? Mathematics, we don't always see it every day in class because we have to learn foundations, but mathematics is a language for the patterns and relationships that we discover in nature, right? And so Benjamin Banneker wanted to understand astronomy better, so he educated himself on mathematics. The deeper you get to go in mathematics, the more you get to learn, okay? So that's who we're celebrating this week is Benjamin Banneker. Now let's get back to our regularly scheduled programming. Alright, if I remember correctly, in this class we wrapped up everything with activity 3.1. Does that sound correct? Yes? Okay, so here's what I do want us to do. Open up the book to M1-34. Did we fully answer questions 2, 3, and 4? Check it. I don't think we talked about 4. Maybe we talked about 3. We did? I just had y'all write it in there? Okay. So, we went all the way through this. Alright, this was what I didn't have in the slides. I don't know how I missed it yesterday. What I do want to remind you is this, okay? As a part of what we're studying, to understand relations better, remember, for relations to be equivalent, what has to be true? For relations to be equivalent, what has to be true? Same inputs and the same outputs, right? So we've got to recognize that we need the same inputs and the same outputs. The same inputs map to the same outputs. For example here, -1, 1.73. -1, 1.73. That point is right here on the graph. -1, -1.73. Right here on the graph. 0, 2. 0, -2. Okay? And I didn't bring this up because I know we didn't answer number 3. Well, we didn't see number 3 yesterday, and that's what I'm going to talk about. How could I show that these points go with that equation for V? Okay, what do you mean by that though? So, I don't need the graph if I'm looking at the table and the equation. We're going to talk about the graph in a second. Guys, we talked about this yesterday. How could I show that these points go with this equation? Substitute them in, and it should make the equation what? True, right? And there is some rounding with it, but we do want to, so there, it probably will say false, but if I put in -1 squared plus 1.73 squared equals 4, it'll be close to being true, there's just rounding error. Do not forget that it should make the equation true. Yes, Jalen? So, you see how this is x? So that's going to be substituted in for what? For x. That's all I'm saying, right? X is my input, and if we have a function, which this is not a function, it's only a relation, we can talk about that more in a second. But if I substitute this in, then I'm going to get out my y. Okay, so looking at a function, so let me go back to a function. Yeah, this works. So in this case, right, if I substitute in -4 for what? X, what am I going to get out? The output of what? Which is, and for -4, the output is. So let's say I substitute -4 in here. See how I'm letting -4 take the place of x? So it's f of x equals x plus 5 times x plus 1. You see how that -4 is taking the place of x? So that's my input. Equals -4 plus 5. X is being replaced by -4, my input, times -4 plus 1. What is -4 plus 5, y'all? It's positive 1 times, what's -4 plus 1? -3. And what's 1 times -3, Jalen? Right? See how this input resulted in this output. Make sense? That's all that is. And the function notation is why we like that, because it shows me my inputs with my outputs. If I just said y equals, I wouldn't know what the input is. But now I have input and output. So good question. Alright, what other questions do we have? Okay. So the last thing I want to point out is this. Oh no, two things. If I go to try to graph this on the calculator, could I use the function operation on the calculator?
Yes.
I hear some people saying no. I hear more no's than yes. Can someone tell me why they're saying no? It's not a what? Not a function. How do you know it's not a function? So right here, Jamarcus, you see how that x equals -1, that's one input, right?
Yeah.
But how many outputs would it have?
4.
Just for this -1.
2.
It only has 2. But if it has more than 1, it's not a function. Does that make sense?
Okay.
If it's not a function, it is still a what? Relation, because it's a mapping of inputs to outputs. So we couldn't use function here, but I could use relation when I get to that calculator. So don't forget that. You can type in x squared plus y squared equals 4, and it would give you that graph. So number 3, how do you know which relations are functions and which ones are not functions? So there's a couple of different things that you can do when we look at it algebraically or graphically. So I'm going to talk about this in a second. But at the end of the day, what's that core definition for a function? Each input maps to one and only one output. So if it is not a function, the definition, right, would be that at least, so it only has to be one, but at least one input maps to what? No, for it to not be a function. So it just has to be more than one output, right? And it only has to be one input doing that, right? At least one input maps to more than one output. That is the definition, right? For it to not be a function. So to not be a function, at least one input maps to more than one output. At least one input maps to more than one output. Many of us need to make sure we have that in our notes. You might already have something like that, so you don't need to write down, but we gotta have that written down somewhere. These are the last couple of details from this part of the lesson. Okay, that's what I'm saying. If we already have it down, then we're good. I just see some people still writing it down. Now, it's a little bit different, I thought. Yeah. So I think what I said yesterday, to be a function, each input maps to one and only one output. Notice I'm giving, so if that's the definition of a function, to not be a function, at least one input maps to more than one output. So if you should have that definition of a function, but this would also be what disqualifies it as a function. And so I do want to look at this in a table really quickly. In a table, how do you know at least one input maps to more than one output? This would also be able to go under number 2. What tells us in that table with x that that's not a function?
Because we know that like the next one on the y column, it's not like consistent.
Well, it doesn't have to be consistent to not be a function. Jose?
You got 2 y.
Good thought. 2 y-intercepts, partially. Guys, think about the definition.
There's 2 of the same y.
2 of the same y?
And x.
Yeah.
Well, remember, it's not the output that matters. In the sense that you can have the same output. Okay?
It repeats x multiple times.
The x repeats and has what has to be true about those outputs? The outputs are these outputs? They're different. That one input is getting how many different, or how many outputs?
What they are right now.
Huh? Say again. Okay. I want to contrast that, so I'm going to come back to this tabulator, but based on what I'm hearing y'all say, I want you to look at this. This is a quadratic. This is literally just y equals x squared. Notice right here how I have the same output, right? But it's different inputs. The input of -2 maps only to what? Does that -2 map to anything else? No. This input of 1 only maps to 1. Notice it's about the input can only have one output. But you can have a repetition of outputs. Does that make sense? So that's what we want to notice. So tabularly, literally, it is the definition, right? The table is the easiest way to see that definition. But under number 2, right? One input has multiple outputs. There's nothing really else you can say with the table.
Write this on 3-2? Or just,
This would be, oh yeah, is this number 3? Yeah, under number 3. So I'm giving you more clarity on the different representations, right? If at any time one input maps to more than one output, it's not a function, but we can clearly see that on the table, right? If at any point one output maps to more than one input maps to more than one output, it's not a function, but that's how we see it on the table. Under number 3. Yeah. You could go off to the side if you need to, or go above it. I'm just adding clarity to those different representations. I'm going to come back to this in a second. Okay. I want you to look at this graph right here, R. That's exponential. Any questions about that? Are we good with that graph being exponential? Okay? This is a function, right? Exponentials are functions. How can I tell graphically that it is a function? Okay? I need eyes up here paying attention to this. So I want you to contrast the circle here that's not a function. How do we know it's not a function? Versus this exponential that is a function. What are we seeing that's different?
This one's constant and it's adding.
Anybody want to add on to or push back on this is constant and adding? Okay, we're going to talk about that in a second, but I want to talk about that idea of it's constant and adding. So remember, it's exponential, so it's constantly multiplying. Say that again though, David. You said it's only crossing through the, when you say line, do you mean the curve, the exponential curve? So right here, if I look at an input of 1, how many outputs do I have? Only one output, right? At this input of 2, how many outputs do I have? Just one. So when I draw a vertical line, that vertical line hits how many points on the curve? Only one. So one input has one output. When I look here though, and I draw a vertical line, one input has how many outputs? 2. This is known as the vertical line test. This is a very common way to test if it's a function. The vertical line test, if a vertical line, which by the way we usually abbreviate to VLT, so if you see that abbreviation, that's vertical line test. If a vertical line intersects the relation at more than one point, not a function. And so we do want to notice if that relation, or if that vertical line intersects the relation at more than one point, it is not a function. Because that means that one input would have multiple outputs. Still under number 3. And so notice, all of this is adding a quick way to check this definition. This is the definition of when it's not a function. At least one input maps to more than one output. Tables, you can literally see that. Graphs, that vertical line, if it intersects the relation of more than one point, that means that that one input has how many outputs? 2 in this case, right? But it could have more than 2. And we will see some relations that do that later this semester. What are your questions about this at this point? Okay, I'm going to let y'all continue to copy that down under number 3. I think the next thing that we need is we're going to go to Clever. Before we do that though, put your book in your backpack, get out your iPad. So put your book up, grab your iPad. Alright. Oh, we don't want all those. Who do we not have today? We don't have Haley, Pam, or Preston.
I don't have it.
Alright, so these are our new randomly generated groups. And so we'll go ahead and move to our groups. Grace, Naisha, Treyana, and Mickey up here in group 1. Jacoby, Lily Kate, Tevin, Marshall here in group 2 for me. We got new groups. Come on, we gotta start moving. Rakai, Jayla, Eliza, Jamarcus in group 3. How did that happen? Group 4, Ethan, David, Juan. Group 5, Phoebe, Jose, Desiree. Group 6, Sanaya, Shania, and Hayden. Group 7 is Z, Jalen, and Miracle. Alright, let's move to our new groups. Alright, so we have people that we're going to be working with today. Get out your iPads. I will come and work with those who don't have an iPad when we get there. Okay? But for now, on your iPad, go to Clever. You're going to select the Carnegie Learning portal. It is a black background with a C there, or CL, I believe. So go ahead and move. Sanaya, what you doing?
Oh my man, I'm so sorry.
Okay. Alright, so at least try to look on with somebody. If you see someone at your group who doesn't have their iPad, show them what you're doing. So turn it to help David and P1 out. Okay, so get into Clever. Log in with username, yep. So, yeah, just kind of try to follow along here. So, what I would do if I were you, so it's Carnegie Learning, or it's called MATHia. Keep scrolling down. Trying to see it, keep going. There it is. If you go to more apps at the very bottom, what I would do is I would heart the CL for Carnegie Learning, and that'll move it up to the top, but you can click on the Carnegie Learning, all the way at the bottom. Heart that CL for Carnegie Learning, and then click on it, because we will be using it throughout the semester. You might want to turn the brightness up. I got you. Alright, once you get there, you should see a blue icon on the far left side. Click on it for me. Wait, that did not sound good. Don't do that. It'll just keep resetting. Just wait a second. The internet is not the best. Okay. Do you have to click on materials first? Okay. So you click on materials and then go to MATHia is what we're looking at there. Now, sorry, I should have said this. Did anyone look at what materials was below MATHia?
It said it is.
It said e-text. Your textbook is also loaded onto that website so that you can always access your textbook through the MATHia materials. Now, what I'm going to do is give you about 15 minutes to get started on this Unit 1 linear, exponential, and quadratic function. So click on Let's Go. If you don't have your iPad, it is going to be on you to do this during enrichment. Notice I'm only giving us 15 minutes to get started, but this is to help us get started with using MATHia. Now, I'm going to show a little bit on the board. If you are good to go, you can ignore me. But if you are missing your iPad,
When we get to the part where we click, let's go again.
yeah, click on Let's Go again. Yep. Okay. Content. So this is how mine looks. This is not what yours will look like. But I made a unit just for y'all. And I will point this out. This getting started here, okay? The getting started is not a part of the math, but the getting started is designed to help you understand how the MATHia works, okay? And so you're going to want to watch these videos. If you have headphones, you can connect your headphones right now though. I would just turn the audio down low. Keep the audio there so you can hear, but turn it low so that you can watch it. You're going to have times when you need to watch the videos to be able to answer the questions. Because I'm going to go out on a limb and say no one here knows how many routes or how many streets there are in London that taxi drivers have to memorize. Is that fair to say? Not Rakai. Phoebe, have you ever learned that detail before? No. No? Okay. So I wouldn't know that either. This is why we're going to use the left-hand side, and you're going to learn about what these little things at the top here mean, stuff like that. Okay? So we have 15 minutes to work through this. We should be able to get through these as, within that 15. I think it took me 8 or 9 minutes yesterday, but you need to watch the videos. You need to learn from it and keep it going. Questions, comments, or concerns? Okay, so just 15 minutes for now. Let's get to work. If you have someone again near you who doesn't have their iPad, at least turn it so that they can see what's happening. Okay? So we got 15 minutes. Let's get to work. Yes, but also I need you to bring your iPad. I need you to finish up this getting started because what are we learning from this getting started? How to use it, right? We're going to use this in class, we're going to use it outside of class, and we've got to know how to use this. They've got gimmicky things, but, hey guys, pause and eyes up here. But they've got hints built in there, right, to help you out. It'll record how much time you spend on it. It'll record how accurate you are with things. But one of the beautiful things about this is you can always redo a workspace. So let's say that you only scored a 73% on a workspace, but I am grading on completion and on accuracy. So half your grade is going to come from completion, half your grade is going to come from accuracy. You can redo it to earn a more accurate score. Hopefully we're starting to see, right? They've already shown you multiple ways they're going to try to teach you how to do things. Is that fair to say? You understand they're trying to teach us how to do things? And so I'm going to be here to teach you as well, but there are certain things that are going to help you in this system to be better prepared for understanding checks and for class time, so we are going to use this at times. Two things I want to point out. How many different types of workspaces are there? There's two. The one that you just did where it's just a filled in circle and it's blue until you complete it and then becomes green is what type of workspace? What's it designed for? So we need to pay attention to this. It's not the mastery one. The one that we just did where it's a blue circle and then it turns green once you've completed it. It's just a learning workspace. So, if I can see this real quick. Actually, do I have this up here? So this right here, you see how it's a blue until I complete this section? And it's just full blue, that's it? That's a learning workspace. Meaning that we are just learning about a concept. Well, if you don't learn about that concept, are you going to be doing okay moving forward? No, Mr. Kinney? Good job, guys, right? We're not going to be okay if we don't learn. Notice here, when you finish that getting started, you're going to go to this workspace that's observing patterns. Right here is this one a learning workspace? We can tell right away, is it a learning workspace?
Yeah.
How do we know?
You got the blue thing at the top.
It's got that little blue thing at the top. Also, these animations like this only show up on learning workspaces. They're going to tell you the information you need to know, so you need to watch that video. They're not super long. However, this is a workspace built out of Algebra 1 concepts. Right here, if it'll load. Maybe. Maybe it'll load. Okay. While it's loading, let me talk about this. It is going to be a mastery workspace. You have to continue working until you've shown mastery or until you've worked a preset number of questions. But it's going to grade you on that, on showing that mastery. Here we go. So please notice, and they talked about this in that getting started, you can skip and go straight to the problem. And I had students in the past who have done this, and then they're sitting there like, Mr. Kinney, I don't know how to do any of this. Do you know how you fix not knowing how to do any of this right here? You get a step-by-step example. They walk you through it, and they help you out. You can always go to a sample problem, a step-by-step, or what did that getting started show you that you can always do? It starts with an H. Get a hint. If you have to use hints, if you have to use the step-by-step examples, things like that, it is going to slow down your progress But if you get those hints and you get those step-by-step examples, it's going to end up helping you learn it better, so you're going to be able to move faster. Take advantage of that. Don't just ignore it. All right. So we're going to go ahead and log out of MATHia. I'm going to give you all probably 15 minutes or so tomorrow to work on MATHia. We're going to take probably 15 minutes or so most of the days this week. And then whatever you do not finish in class this week, we're going to finish for homework over the weekend. Okay? So 15, oh wait, not done with the iPad, sorry. Just logging out of MATHia. Because we are still going to go to Desmos. Alright. So, if you don't have an iPad, you can still work on this with somebody who has an iPad. Everyone has a sheet of paper that they need on the desk. And I'm going to go through to clarify some of these things in a second. So follow the directions on the board. Go to student.desmos.com. If you already have an account, bet. If you don't have an account, use your TCSS email and password to create an account. Okay? The code is up there. Hold on, before you enter the code, sign into an account. Before you enter in a code at the bottom, sign into an account. I would personally sign in using your email. Before you put in the code, log out of here. There should be. It'll save your progress. Don't continue without signing in. Sign in with Desmos. If you need to create an account, there's an option. Nope. Go to student.desmos.com.
It doesn't.
Is it all caps?
You have to enter the code first and then I tried it.
It didn't work?
No.
If you... Okay, to go back, it'll give you a chance to create an account then. So type in the code. My bad. I thought it would give you a chance to create an account right away. So type in your code. Make sure that you create an account before you get past that next screen. So 2MGQXS. Did you already sign in? Yeah, so create an account. Once you put the code in, hit join. But then make sure you create an account if you do not already have an account. And I would use your school email and password. If you do not create an account, you will have to start over every time you log in. That is why you want to create an account. Do I need to leave this code on the board, or can I move on? Anybody need me to leave the code on the board? Okay. Give me a quick show of hands if you need me to wait before starting this lesson, or have we logged in? That's right. All right, can I get someone to read the first objective on the board, please? The first objective. Go, Jalen.
I can identify the three forms of quadratic equation.
So, we're going to talk about this in a second, but I want you to notice, Jalen, now can you please take your headphones out? Thank you. There are three different forms of quadratics that we'll primarily use. We've only really used one linear form, but there's more than one linear equation, there's more than one exponential, but we are going to focus on all three forms of quadratics. And then, can I get someone to read the second objective? Go for it, Lily.
I can identify the features of a parabola based on the form of a quadratic equation.
So what are some of the features of a parabola that we could look at that we already know about, right?
Yeah, right there.
What's that right here?
You know what I'm saying?
I know, I do know what you're saying. What is she saying, guys? Concavity, right? Concave down or concave up. David, you said one. What was it?
Vertex.
Vertex. Anyone know any other features that we might want to look at of a parabola?
You got a line of
Maybe a line of symmetry, right? And there's two more features that we're going to want to know based on the equation. So hear me clearly. We can always see these features just on the graph, but we need to be able to see these features just from the equation as well. And so the other two features we actually look at regularly with all types of functions. They're the x and y intercepts. We're going to want to be able to recognize all of those features just from the equation. And so here's the starting. You should be able to see this once you're logged in. This is also on the sheet of paper. So everything that is in Desmos, for the most part, I have put on the paper because I want you to have a physical copy. You can always log back into Desmos and see this and play around with it to help you study. But when we studied linear functions, there were three different equations. The slope-intercept form, right? Y equals mx plus b. We've talked about that pretty heavily recently, right? In fact, the bell ringer just today. There's something known as the point-slope form. We haven't talked about this one much because it's not a focus or a priority for this class, but this is a really good equation. Notice I don't have to use the y-intercept here because I can use any point and the slope. And notice there's m times here, multiplication being that repeated addition. And what's this form again? Standard form. We talked about that with the to use or not to use algebra, that very first lesson we did with this unit. So please note each of the values, not the variables. What are the variables in each of those equations? X and y. The variables are x and y. The values, right? A, B, and C here. M, my slope, B, my y-intercept. M, my slope, x1, y1, that's a point. Each of those values can be clearly connected to something in the graph. Okay? And so what we want to do, and I've given the examples here, what we want to do with quadratic functions, there's three different equations as well. These forms are the vertex form, y equals a times x minus h squared plus k. The standard form, y equals ax squared plus bx plus c. And the factored form, a times x minus r1 times x minus r2. Throughout this exploration, your job is to determine how the different values in these equations connect to the graphs. Your job is to figure out how these different values connect to the graph. And so, the very first section you're going to look at is the vertex form of a quadratic equation. Let me show you on the board really quickly what this looks like. There we go. So, notice this is where we are. Please pay attention to the directions. And again, this is where even if you don't have an iPad, you can look on with somebody. What does the very first set of directions say to do? Adjust the value of what? A. Are you going to adjust the value of h or of k? No. Please follow the directions. The h and the k show up later. Notice, and I will point this out, which form are we looking at in this very first exploration? Look at the information on the sheet. The a times x minus h squared plus k.
Vertex one.
How did you know that?
Sure, on the paper.
Okay, if you look at the directions on the paper, it has the different forms, but also in bold, what does it say? Which form?
Vertex one.
Vertex form. Guys, you've got to study these equations. You've got to know these equations. What we're exploring right now is what do the different values in that equation mean and tell us about. So, all we're doing right now is adjusting the value of A. And so you're going to grab this dot here, and you're going to pay attention to what is happening to A. Use as clear and as precise mathematical language as you can. Please note, is there a pattern here that you might be able to discover and talk about? We should be looking for those different pieces of the mathematics. And so there's a pattern and relationship. Discuss it. Talk about it. There is space for you to write your information down on your sheet of paper, but there's also space to type it in here. Actually, no, there's just more directions about it. So like, notice the second slide just says, when the value of A is positive versus the value of A is negative. That's what you want to be thinking about. When the value of A is between -1 and 1 versus less than -1 or greater than 1. That's what you want to be thinking about during that exploration. I'll be coming around and listening in on conversations, but I want you to play around with it and find these different values. when you get to the end of the vertex form, right here, you'll see a table where you can actually enter the values into this table. This is the same exact table that's at the bottom of that page. Okay? So we're going to work on identifying these different features through this exploration. What are your questions about the exploration? Is this supposed to be a silent activity? Explore for a second. See if you can find a pattern for the directions on that page, but then talk with each other. The more ideas you start talking about, the more you start generating that mathematical language, the better you're going to understand it. All right? So make sure you're on page 2 or slide 2 of Desmos. And what are we adjusting to try to find a pattern? A. Okay? So let's get to that work. So let's start adjusting those sliders. Yes, sir. Right? To make sense out of what was happening. And y'all notice things without me having to tell you stuff. What were some of the conversations that we had just looking at slide 2? What were some of the things that we originally said about that value for A? Guys, Paul, this whole class discussion, you'll have time to write in a second. What are some of the things that we noticed about the value of A before I even said anything? Tevin? Well, before right now, right? But, so I'm saying, like, what did y'all talk about in your small groups? Yeah. Okay, I want to push on that language a little bit. When it's positive, it's concave down. Can anyone add any more clarity to that? Oh, when the parabola, right? Guys, don't use the word it. It is unclear. The parabola, or I guess, well, is the parabola positive? What's positive? When the A value is positive, the parabola is concave up, right? Those are very different things than it. When you said it earlier, it almost sounded like they were the same thing, right? Okay, so we have to be clear with our mathematical language. When the value of A is positive, right now A is positive, that parabola is what? Concave up. When the A value is negative, the parabola is? Concave down. Oh, that's true, right? Notice when A is 0, what do we have?
A line.
A line, not a parabola. So what's the difference maker? The positive versus the negative. The negative was when it was concave, the parabola was concave down. When A was positive, the parabola was concave up. Jamarcus, you were talking about it earlier that at certain times it was bigger. What did you mean by bigger?
It explained it when the number it was a bigger positive number.
Okay, so when you say it expanded, so like, what do you mean there? It is what?
Wider.
Is that wider?
No, I mean.
And so we want to be clear with our language, okay? So you were saying it's wider. When was the parabola wider? When A was what? Closest to. What was the parabola widest? When A was what?
Close to 0.
Close to 0. Right? The closer A got to 0, the wider it appears. So one thing I want to caution you, and I know 100%, this is not what we naturally see. Hear me very clearly on this. But it is not getting wider. What's actually happening is it's either being vertically stretched or compressed. But if I push something down, what's also going to happen? It's getting wider. What's mathematically actually happening there is when A is closer to 0, that parabola is getting squished down, so it looks wider. Does that make sense, Jamarcus? And this is one of those things that you're not going to understand 100% right now, but we will study stuff later that will explain that. But when A is larger, it's going to what? It's going to vertically stretch. So those are the things that we would want to note. Right here, under the vertex form of a quadratic, right, the value of A, we need to talk about when A is positive, the parabola is what? Concave up. When A is negative, the parabola is concave down. That's it. Concave down like a frown. One thing I will say is, an easy way to indicate A being positive or negative is this. What does that inequality say? A is greater than 0. What numbers are greater than 0?
Everything.
What type of numbers in general?
Positive.
Positives, right? So if I'm talking about positive numbers, I can just say A is greater than 0. So when A is greater than 0, remember those are my positives. The parabola is concave up. Now, could you just leave it as when A is positive, like with the words? 100%. But we're going to see A show up again and again. I would start to think about that notation. In a similar way, when A is less than 0, the parabola is concave down. Okay, I'm not going to write that right there. Get those notes down. So notice, oh, we're still writing because I didn't write the second part, my bad. Quick show of thumbs up when we're done writing the part about concave up and down. Yeah, Grace, thank you, thank you. You're done? Okay. Alright, so pause on the iPads. We need to pay attention up here because I do want to note this notation as well. What is this saying? Okay, -1 is less than A is less than 1. What does that really mean though? It just means A is what? It's between something. A is between? Not 0 and 1. -1 and 1, which it's close to 0, right? If A is between -1 and 1, the parabola is, what did I say that word was? It's being compressed, right? Parabola is, and I will add this note here. I keep talking about it like this and this. It's vertically compressed. Someone in the door? Okay. Is vertically compressed. And so I will add this note in. This is what Jamarco is saying. It looks what? Wider, right? So it's vertically compressed, which is why it looks wider. And so notice that's just if A is close to 0. Okay? If A is greater than 1 or A is less than -1, so the further we get from 0, that parabola is going to be what? So as we get further from 0, the parabola is not being compressed, it's being stretched, vertically stretched. That looks narrow, but it's actually longer. Please note, did you use this language originally? But did you see these ideas without me having to tell you? Why is that? What is math? It is a language, but that language is to describe what? Patterns and relationships. You can notice those patterns and relationships on your own if I set you up the right way. So you don't have to have it perfect, guys, but I need you to look into that pattern of that relationship, describe what's there, and what am I going to do? I'm going to give you the language, the precise language to talk about it. Might even include some of those more casual terms to explain it, but we need that precise language to describe these things at the end. We gotta study that language to be able to use it more effectively in the future. Okay, we only have 4 minutes left. Quick show of hands if we got to H and K. So 1, 2 groups, but not done with it yet. Okay, so let's do this. Continue to explore H and K. I will tell you when we have 90 seconds left so you can start to pack up. But let's continue exploring H and K until that 90 seconds to go. Yes, you can just hit that little home symbol and it'll go right back. What did you do to your... Oh, stop. Look right here. How did you do that? Okay, so K needs to be between -10 and 10. You were for real exploring, but that's going to get you messed up. Why is yours 8? Right?
I was just looking for it.
So notice that relationship. Notice what's happening with H and K. Once you think you know what's happening, right, go to the next slide to see, oh, by the way, we're on slide 4, so that when you go to the, so read that direction up there. When you go to slide 5, think about these questions. Okay? So,
You sketched it.
I did not catch it. It hit me in the shoulder.
why are we throwing it? Stop. Hey, let's explore. We got H and K to explore. Let's go. Because you took out the H and K. You need your H and K there. Yeah. Uh-huh. H and K. Oh, there it is. Oh, now, you did something else. Oh, that's good. Yeah. Yep.
It contains
We're gonna do, we should wrap this up tomorrow. If not, we'll wrap it at the very beginning of Thursday, and then we'll do something out of the book that builds on this information. I'll let you know at the end of class, depending on what we get.
You got, I don't know, just charged the power. Because Desmos got her own. Yeah.
Okay, so we do have 90 minutes left at this point. Seconds, okay. I feel like there's been some good learning today, but what are all of you capable of more? Do not bank on lots of time in class on the Carnegie Learning stuff. I forgot that I have the Carnegie Learning being due all the way through that detail by Friday. I may change it, I'll talk with you more, but I would go ahead and start working during enrichment on the Carnegie Learning MATHia stuff. Please notice we have plenty of time to get it done. Make sure you have a charged what tomorrow? iPad. Charged during enrichment, whatever you gotta do.
Leave it right there.
You always have, this was a good learning today? I will say this, while there's been some good learning, I need some better active collaboration, talking from more people during whole class discussion. A lot of us are starting to talk well in groups, but not well during whole class. Have a good rest of your day.
What's what you doing? Oh, okay.
Either I lost my candy here or somebody took it.
Or you gonna put that?
I don't know how to.
David, you shut up.
Alright, okay. Oh! No, the he said, no, the he said.
Thank you, Shania.
My dude.
Oh, yeah.